We're having a similar problem as Monday, so I'm just going to try to put my laptop here and get the angle right. It might be better if I put this in the center. I think. Sorry for the intrusion. It's bad glare, huh? Is my microphone on? Yes. Okay. Okay, so we were last discussing level sets and gradients, right? And our goal is to kind of define what it means to describe a tangent set to a level set of a given function, right? And on Monday, we discussed a bunch of examples of level sets for various functions that were somewhat easy to visualize. And then we gave a definition of what a tangent set at point P on a level set. That is to say, let me remind you. The tangent set of the level set M given by f of x equals f of p. Remember, we defined this level set through a point P in the domain of f, right? We produce a real number, a constant that we set the function equal to, produce a level set. Yeah. At point P, is the set of points x in Rn satisfying I should write this on the next line actually. Gradient of f, sorry, capital F, evaluated at P dot x hat minus P hat is equal to 0. Right, that is to say, the gradient defines a normal vector to the level set M at the point P when we evaluate the gradient at P. Right? And we're just taking all the vectors that are perpendicular to this normal vector, the gradient. And that gives us the definition of tangency. Okay. So, in particular, note the following. Note, if M, our level set, is the graph of a continuously differentiable function. Just want to make sure that I'm still in good parameters here. There's no audio on the Zoom. Okay. Sorry. Let's see here. I don't know how to do this test. Oh, never mind. You had to restart your Zoom. Okay. Great. Sorry, everybody. Good, as long as we can all hear. Okay, so if M happens to be the graph of a continuously differentiable function, that is to say, remember, M comes from the level set of some graph of n variables. It might happen that M can also be described as the graph of a continuously differentiable function. And in that case, this definition of tangent set agrees with our previous definition. Of tangent set to a graph. And the point of this remark is that we're going to make a bunch of different definitions of what a tangent set is, depending on what type of object we're looking at, whether it's a graph of a function, a level set of a function, and then soon we'll talk about how to parameterize a surface and describe the tangent set to a parameterized surface. But the point is that when we are in a situation where all three of these interpretations can be put upon the situation we're in, all these definitions that we're going to give agree. They give the same set. Now, it might be the case that we have some level set that is not the graph of a continuously differentiable function. And in that case, our previous definition for tangent set to a graph doesn't make sense, right? That was the requirement that we have a continuously differentiable function if we want to describe the tangent set to a graph. So I guess what I'm saying is, yeah. Previous definition. Let's see, this was last week. The first time we saw a definition of a tangent set to a graph of a continuously differentiable function. Here we're just talking about a level set. And those are different. Remember, a level set is a cross section of a graph or function under the right circumstance. That's what we talked about last time. Now, it might happen that that cross section is also the graph of a continuously differentiable function, but not always. Okay. So let's do some examples. I think this will illuminate where the similarities and differences lie. Okay. When n equals 2, that is to say, f is a function from R2 into R, continuously differentiable. the definition of a tangent set to level set M given by F evaluated at A comma B. Oh, sorry, I really should say this in the opposite order, right? Given by F of X comma Y is equal to F evaluated at some specific point, A comma B. That's how we specify this level set M. In this scenario, if I look at some level set of this function F, what will the tangent set be? This is kind of a dimensional analysis thing, right? Where we have a, sorry, maybe I should mute it. Okay, you can still hear me, people on Zoom, right? Didn't mute my microphone. Okay, so right, this is kind of a dimensional analysis problem that I'm asking you to think about here, right? Where does the graph of F live? R3, yeah, right. It's the sum of the exponent on the domain and the range. It lives in R3. It's a two-dimensional thing. It's some surface, right? Since we know it's continuously differentiable, when we take a cross-section of that surface, what do we get? So a plane is a two-dimensional thing. When we take a cross-section of a two-dimensional thing, we get something one-dimensional. It's a curve of some kind, right? That is to say, because F is continuously differentiable, when we look at the level sets, we'll get curves, right? Okay, so what should the tangent set that we defined give us? Say that again. Somebody said something. Somebody want to say something? No. What is a tangent set for a curve? Yeah, a tangent line. Exactly. So the tangent set to the level set M given by this equation is just a tangent line to the level curve M at point A comma B. Yeah. Mhm. Okay, so the graph is in R3, which means it's a two-dimensional thing. Then when we take a level set, we're intersecting that surface with a plane.
Wait, so you say it's a two-dimensional thing, you're talking about the third variable would come from the start.
Yeah, right. So when we just look at F of X comma Y, that is equal to Z, right? That's our third variable. Now we're fixing Z. We're evaluating F at some point A comma B and fixing a value for Z. So now this just becomes a function of a single variable if we solve for Y, right? So that gives us a curve. So yeah, this is somewhat confusing, right? We could talk about the tangent set to the graph of F at the point A comma B comma F of A comma B. Or we can also talk about the tangent set to the level curve given by this at the point A comma B. Is that okay? Okay. Yeah, so this is a key example. Really think about this. Okay. I want you to become very comfortable with determining what dimension thing you're thinking about when you working with level sets and tangent sets. Okay,
So you're fixing Z and you're also fixing Y.
I'm not fixing Y, no. So remember, a level set is just a function set to a constant. And here I'm generating that constant by plugging in a value a comma b into f, because it's a real value function. So that gives me a constant. So this is what I'm setting z to be equal to here. That is to say, I'm slicing the graph of f at this constant z value. This is a plane defined by z equals f of a comma b. Okay. Yeah.
So are the cross sections.
Yeah, exactly. Right. So when we take this cross section and we describe the tangent set of the level set, we just get a tangent line. Yeah. Good. Yes. Yeah. So it's in a copy of R2, namely the plane z equals f of a comma b. Yeah, so it exists in R3, but it lies in this plane z equals f of a comma b. Yeah, that's right. Okay. Okay, so right. Let's write this out explicitly in terms of the formula that we have, right? This is, say, we get the gradient of f evaluated at a comma b dot xy minus the point a comma b. Well, this takes a fairly familiar form, right? Well, let me write every step of this just so we get really comfortable here. This is the gradient of f evaluated at a comma b, right? I take the partial with respect to x and evaluated at a comma b, partial with respect to y and evaluated at a comma b. Dot its vector x minus a, comma, y minus b. Okay, we get as partial x evaluated at a comma b times x minus a plus partial y evaluated at a comma b times y minus b 0. Hopefully this convinces you of everything I just said, right? This is an equation of a line in you could think of it as getting point slope formula. Right? Now remember, if you look back to our theorem from Monday, we must have where gradient of f AB is not equal to the 0 vector. Somebody explain to me why we insist on this. Talk about this a little on Monday. Think about it for the first time now. Exactly. If we allow the gradient to be 0 at the point we're interested in, this gives us no information. It doesn't describe the set of perpendicular. Well, it doesn't. Say that more carefully. Taking this dot product, if the gradient is 0, tells us nothing about the vectors that are tangent to the level set. Right? So exactly as you were saying, we just insist that the gradient not be 0 at the point we're interested. Okay, so let's continue. Now, tell me some things about what happens when n equals 3. And I'll set you up here. We'll take a point p hat. It's called a comma b comma c. And again, insist that the gradient of f evaluated at p is not equal to the 0 vector. What do we get for the tangent set? Then the tangent set to the level surface m given by f of x comma y comma z is equal to f of a comma b comma c is what do I get here? For the tangent set to this level set, I guess I should say at point a comma b comma c is given by what? Maybe I should be slightly even more explicit here, right? When n equals 3, what I'm saying is f is a continuously differentiable function from R3 into R, right? F has 3 variables, 3 inputs, and a single real valued output. So what do we get for the tangent set of the level surface? I'm giving you a hint here. I don't say level set, I say level surface. Yeah.
Function is within R3.
Yeah, it's a plane. Exactly. Right. So the graph of this function f lives in R4. It's a 3-dimensional thing. We take a cross section of it, we get a 2-dimensional thing, a surface, right? A level surface. So the tangent set to a level surface is a tangent plane. Good. What's the equation? Yeah, exactly. Let's just cut to the chase. You'll recognize this as the standard equation for a plane, right? The standard equation for a plane that goes through point A, B, C with normal vector fx, abc, fy, abc, fz, abc, i.e. the gradient. Yeah. Yeah, sure. So we have a function of 3 variables with a real output. So when we look at its graph, well, I shouldn't say look, but its graph lives in R4, and it's a 3-dimensional thing. Since we're assuming that it's continuously differentiable, when we take a level set, it's going to be 1 dimension lower. It'll be a surface. That's why I say level surface here instead of just set, giving you a little more information there. Okay, so what we would expect is that the tangent structure, a tangent set to a surface should be a plane. And applying this formula, oh, I erased the formula, but the formula that you said, the dot product, gives us exactly that, the standard equation of a plane. Okay. This is just, yes,
So you said.
Mhm. yeah, so then we just call it something, one dimension higher. Yeah, a tangent. But yeah, tangent set applies to all these structures. We say tangent line and tangent plane just to kind of ground ourselves, right? These are the structures that we're familiar with. So when that situation arises, it's kind of nice to remind ourselves that we're really just looking at generalization of a line of plate with these higher and higher dimensions. So these examples are kind of generalities, right? We didn't actually compute any specific gradients or any functions, right? So let's revisit some function that we've dealt with a fair amount already. Terrible. Oh. Okay, so my marker's dry. So let's consider f of x, y. I'm sorry. I'm just gonna have to get some more. So let's look at what is rapidly becoming our favorite example. F of x, y equals x squared minus y squared. This saddle, right? What's the gradient of f in this case? What do we got here? 2x, comma, what's the derivative of? Yeah, negative 2y. Okay. So this implies gradient of f is equal to the 0 vector only when x comma y equals 0 comma 0. That at any other point besides 0 comma 0, if we take the level set through that point, we should get a smooth curve, which we saw, right? This is all the hyperbola that we drew on Monday, right? And of course, at the point 0 comma 0, we get two lines crossing, right? Which have a singular point, a sharp point, where you can't define the tangent line. It's ambiguous what direction you're going. Okay. So f is continuously differentiable. And the gradient of f is not equal to 0 comma 0, except at 0 comma 0. All right. So all level curves f of x comma y equal to f of a comma b are smooth for A comma B not equal to 0 comma 0. I'm saying the same thing over and over again in a different way each time, right? This is what our theorem says. As long as we're continuously differentiable and our gradient is not 0, then the level curves are smooth for each level curve through a given point where the gradient is not 0. Right? Okay. So let's look again. At f of x comma y equal to 1. Right, not negative 1, 1. Okay, we graphed this on Monday, right? This is a hyperbola. One. Okay. So let us add some decorations to this drawing. So why don't we look at the point 1 comma 0. We have the gradient of f evaluated at 1 comma 0 is equal to what? 2 comma 0, right? Just plugging in x and y. Okay, so here's my point 1 comma 0. Okay, and my gradient vector is this, right? Gradient of f at 1 comma 0 equal to 2 comma 0. All right. So in other words, how do I define? We've just said this. I'm just trying to reiterate it. How do I define the tangent line to this level curve at this point, 1 comma 0? Well, just graphically, what is the tangent line here? It's a vertical line parallel to the y-axis, right? Just like we said, the gradient is perpendicular to the tangent line, right? Which, going back to the first week, this is one way to specify a line, right? We give a point that the line goes through and a normal vector. It turns out that for a continuously different function, when the gradient is non-zero, the gradient gives us a normal vector along each point of the level curve. Okay, so let's look at another point. At the point, oh, let's say root 5 comma 2. Gradient of f evaluated at root 5 comma 2 is 2 root 5 comma minus 4. Okay. So first of all, what's the significance of the point root 5 comma 2? It's fairly arbitrary at first glance, right? Yeah. Yeah, exactly. It lies on this level set. It lies on this curve, right? So note. 5 squared minus 2 squared is equal to 1. Implies the point √5 comma 2 lies on the level set. F is equal to 1. So let's draw this point approximately. This is somewhere like here, say 5 comma 2. We know it's on the curve because equals 1 when we plug it into the function x squared minus y squared. Good. Okay. And let's do a sketch of our gradient vector. So it's something like this. Right? This vector gradient of f at √5 comma 2 equal to, what did I say? 2 √5 comma -4. And again, we take the line perpendicular to that gradient vector, we get a tangent line. Yeah, I'm just plugging it into our formula for the gradient. Yeah, sorry if that wasn't clear. Taking my point and evaluating at this x comma y. Okay. Well, remember, vectors are translation invariant, right? So if I move this over to the origin, this gradient vector, this is schematic. I didn't draw this to scale, but this is supposed to go out to √5 and down, since the y coordinate is -4. Right. So if I translate this vector over here, I get this. Right. That's just from the coordinates, is how I know it points in that direction. Okay, that's why we go back to the level curve example, because even in 3 dimensions, I'm pretty hopeless drawing, right? Hard to actually indicate an orientation of the vector, unless you're decent with perspective, which I'm not. But here it's fairly clear what directions the gradients should point, right? Just by the coordinates. Okay. Good. So just to complete this example, let's actually write the equations for these 2 tangent lines. This line, this line. Okay. The tangent line to the level set f equals 1 at 1 comma 0 is given by, I'll write the definition, the gradient of f evaluated at 1 comma 0 times, terrible mistake, dot product with x minus 1 comma y minus 0. Right? So that is to say, this is equal to, we calculated our gradient up here, 0 dot minus 1 comma y is equal to 2 times x minus 1. Remember, is equal to 0. So we get exactly what we would expect. The equation of a vertical line. X is equal to something. In fact, x is equal to 1. Right? Okay. For confusion's sake, let's write the equation of the tangent line to the level set f is equal to 1 at the point root 5 comma 2. Tangent line to f equals 1 at root 5 comma 2 is, again, I'll write this out in full. F evaluated at root 5 comma 2 dot x minus root 5 comma y minus 2. Is we calculated the gradient of f at root 5 comma 2 is 2 root 5 comma negative 4 get 2 root 5 x minus root 5 minus 4 times y minus 2 is equal to 0. Okay, just the standard equation of a line. If you like, you could manipulate this, put it in slope intercept form and verify that a line of positive slope of, well, what's the slope here? Root 5 over 2, right? Yeah, is everyone okay with that? I mean, yeah. No need to actually put it in that form. This is what we want to work with most of the time, but just to get you to pull it all the way back to algebra 1. You can verify that this is the most familiar equation of this line that you've seen the most in your lifetime, right? Okay. So, here's a corollary. So let's suppose f of x hat is, again, continuously differentiable. Real value. Function on U, an open subset of Rn. If the point P hat is a singularity on the level set f of x hat equals f of p hat. Before we go on, remind me what a singularity is. And remember, this terminology kind of said it in passing, but we did say it a few times. Do you remember? Singularity. The opposite of smooth. Sorry. Yeah, a sharp point, exactly. It's a point where we can't define a tangent line when we're looking at curves. Of course, this exists in higher dimensions too. It's any sharp point where you can't define a tangent set. Tangent set is not well defined. Okay. Okay, so if we have a place where the tangent set is not well defined, then the gradient of f at P is equal to the 0 vector. Okay, so that is to say, we knew that when the gradient of f at P was the 0 vector, that we couldn't define the tangent plane, or tangent set, I should say. Now we're saying the converse, right? If we know we can't define the tangent set, if we have a sharp point, then necessarily the gradient at that point must be 0. It's going the other direction. Right? So, right. Good. So before we go on, what does this remind you of from calculus 1? If anything. Nothing is the fine answer, but maybe this hope maybe that this reminds you of something. Yeah. Okay. Not quite. It's more closely related to the definition of differentiability. Yeah. Okay, yeah, we're getting closer there. How do you maximize a function in calculus 1? Yeah. How do we find where the extrema might be? Go ahead. Okay. So yeah, that's the second derivative test. But even before that, yeah, the critical points. And the critical points, what are the critical points? Yeah. Where the first derivative equals 0, or you're not differentiable. Remember, last week we were continuously making this analogy that the gradient of f behaves very much like the derivative for a multivariable function. So this kind of motivates the fact that non-differentiability, or singularity in this case, corresponds to the gradient being 0, much similar to non-differentiability corresponds to, or being a critical point corresponds to the first derivative equaling 0. We have a generalized definition of a critical point. So f hat, oh, sorry, not f hat, use f. The real valued function of n variables. A real valued function with domain P, a subset of Rn, a point P in the domain E is a critical point. Sorry. A critical point of F if P is interior to E and the gradient of F evaluated at P is equal to the 0 vector, or a point where F is not differentiable. Okay, so I'm going to insert some parentheses where the clauses go together. Okay, so if P is an interior point and this, and it's the same, we have to satisfy both of these, or F is just straight up not differentiable at P. Okay. Yeah. I was just about to ask you guys that. What do you think it means to be interior? Yeah, that's exactly right. To be inside. Okay, compare this again. This is generalizes fairly a fairly straightforward fashion from calculus 1. Right? So let me just say, call critical points from calc 1. So let's say I have a function f from a closed interval a to b onto the real numbers. Yeah. So here's the graph. Let's say a is here, b is here, and let's say my graph looks like this. F of a here and f of b here. What are the critical points of this graph? Just visually. Function. What are the critical points? Yeah. Yeah, here's a critical point. Let's see, call this C1. Okay, let's say C2. Yeah, I drew this kind of screwy, but yeah, I think you're right. There is the derivative 0 somewhere up here. C3. So these are all critical points. Points F are C1, C2, and C3. What else? Yeah, A and B, right? F is not differentiable at A or B because you have to be able to come from both sides. And our function is not defined to the left of f of a and to the right of f of b. Okay, so A and B. So C1 through C3 are interior with f prime equal to 0. Right? They're interior, they're inside the boundary of the interval. Right? And then on the boundary, we're not differentiable. That's exactly what we're saying here. In the multivariable set. We're inside the domain, i.e. not on the boundary, and the gradient is 0. Or we're not differentiable, which includes all points on the boundary. Now, if I wanted to make this really interesting, I would have done something a little more exotic here and done like a cusp, right? Then we can't define the tangent line here, but we're not differentiable. So C2 is still a critical point. We can't define the derivative there, i.e. the tangent line, when you come from the left, comes like this, and when you come from the right, comes like this. So we can't define it. Yeah. But C2 is still interior. Now we don't say f prime is equal to 0. For C2, f is non-differentiable. Okay. So, higher dimensional example. Okay, so let's let g of x, y, z be equal to z minus 1 squared minus x squared minus y squared minus 1. Okay. let me ask you a series of questions. Sorry. First, find all critical points of G. And let me just reiterate, i.e. points where a level set might not be smooth. Secondly, let's find the points on the level set G equals 0, where the tangent plane is horizontal. And thirdly, I'll ask you to find an equation for the tangent plane to the level surface of G at the point 3, 4, 6. Okay, so let's just take a few minutes and try to work on this alone together. Talking to yourself. This will be good work. Not hearing a lot of talk. No. That's deep, okay, I feel it in here.
Yeah.
Yeah. Yeah.
Set up those little number lines to test multiple. Wait, why? Yeah, Is there another one beside
So, we were, the, I put the points on the 13. How do you? What that is? You're coming down. Radius.
Yeah, that's what I thought too, but he was saying. And then I think.
Are we supposed to rate it like as it was using one?
No. Actually.
I got that.
How's it going? It's going, okay, that's, I think that's positive, right? What do we think?
I think we got 1 point, but we weren't sure like how you decided.
Ah, right, so G is basically a polynomial, right? What do we know about polynomials? In terms of their derivatives. We can differentiate them forever, right? And their derivatives are defined everywhere. So because I didn't say anything about the domain, you can just assume that it's all R3. And then, so you're not going to have any of the critical points that are boundary points, because there is no boundary. So yeah, I think you're good there. You're good for part A.
Okay.
What do we think about part B? Did we get to that part yet? We didn't really say what it means to be horizontal. Any thoughts on that? Well, I'll give you a hint to start. What I mean by horizontal is that it's parallel to the XY point. Yeah, exactly. Right, that describes a normal vector to the plane, right? Which is how we usually want to think of describing a plane by specifying a normal vector. So yeah, that's right on track to what you need for part B. You take, you're looking for the points on the level set B for 0, such that when you take the gradient, it's some scalar times 0, 0, 1. Right?
Okay.
So yeah, I think that's the hint I've been giving. I think you can work pretty well with that. Good.
So why would we do it for X times pizza? So there's no sense in stairs with the.
You said it's
Yeah. Or is that not the point? So. If it's over, is it off?
Okay. So. This is
Yeah, well, yeah. I want to ask her quickly.
tomorrow first thing. Looking at the level. Afternoon, everybody. See you tomorrow. Yeah, we'll go.
I guess now I'm like.
Thank you. No, nothing that we did today. To be honest with you. Yeah, everything up through Monday.
Okay.
Yeah, and I'll make an announcement about that. Yeah, I was blonde for a while and then I dyed it black and the black kind of faded. So accidental highlights, you could say. Intentionally. Yeah, see you tomorrow.